So we'll continue our discussion, and that's a facilitation on Chem 103. We started and we see the course is Introduction to Physical Chemistry. Today's facilitation, we'll review some instruments needed for chemical analysis. We've taken some instruments. We're going to look at principles, methods, and applications of separation techniques. We'll look at the different principles. For instance, when you are carrying out, you find out that the mixture, the different component of the mixture must have different boiling points. So we'll look at that principles. And when we get out of here, when we finish this, we will be able to look at kinetic theory of gases. We'll look at parameters such as mean square speed and the root mean square speed. For the gas pressure, what are the expressions for the gas pressure? We'll derive equation for translational kinetic energy of gases. We'll of gases to try to solve some problem arising from kinetic theory of gases. So now let's start. We are looking at some instruments. So now let's look at chemical parameters. There are many types of chemical instruments. The simple instrument like a thermometer, barometer are all instruments, but there's another one we call analytical instrument will take you to something like maybe a simple analytical instrument can be something like a pH meter, electrochemical apparatus, chromatography, and any other one, NMR, and the rest of them. So like we have melting point tube. When we are coming for practicals, we have Abuja and Lagos Center, the melting point apparatus. So that one is actually used to measure the melting point of a compound. So we have analytical balance. There are two types of balance, and it's called top loading balance, and the other one is called analytical balance. The difference is based on what you call sensitivity. The most sensitive one is the analytical balance. And why is it sensitive? That means if you have fraction, maybe 0.00 up to 4 decimal places, some up to the least of them, up to 3 decimal places can measure. So if it can measure higher number of decimal places, it's called analytical balance. But if it can just measure maybe 1 decimal place or maximum 2 decimal places, then it is called so the top loading balance measure 1 or 2, at most 2 decimal places. Analytical balance should be able to measure at least 4 decimal places. So we have some instrument we use for titration, and that is, the burette, that instrument. That's we can have conduction, geometric titration. We have different types of titration. Conductiometric titration, that means we need to have a conductivity meter. We have pH meter, and we have many different types of titration, but the commonest titration at this level is pipette, the burette, the beaker, the conical flask, the measuring cylinder, and then volumetric flask. That's what you require. Instrument, thermometer. What do we use thermometer for? What do we use thermometer for? So temperature is actually the measure of degree of hotness or coldness of a body. So thermometer measure the Beckman thermometer, determination of freezing point. It can measure freezing point. That is Beckman thermometer. So freezing means that something is changing from liquid to ice. For instance, from water. So example is water changing to ice. So that is an example. So another one is a pH acid or base. That's the strength of acid or base is explained in terms of the pH of the solution. When you look at an acid, is it basic or is it neutral solution? That would depend on pH. And 7, it is said to be acidic. And when it is 14. Hey, that noise is not allowed. Please be matured. Mute yourself. Don't allow me to mute you. We will have a pH meter for measuring the strength of the solution. So we have electrochemical cells. It will also measure the voltage. And we have the barometer for measuring the. We have what we call Oswald viscometer for measuring. Then we have rheometer. It's still for measuring.
No, this one will not be enough. Is
that stupid student there? Let me see if I can. I don't like mood. The way you can have question. I have to mute everybody. So we have Oswald viscometer for measurement of viscosity. So measuring pressure is what? Barometer. The instrument for measuring voltage is what? The instrument for measuring relative viscosity is what? Instrument is not necessary. Burette, pipette, conical flask, pH meter. And of course, I think all of them may be needed. Depends in. Let me use in a simple diatrimetric analysis. So the strength of an acid or a base can be determined. pH meter, barometer, voltmeter, you know, is a pH meter. That is used for the measurement of. So you can have a measuring cylinder. Measuring cylinder is used for measuring volume. So now let's look at one other question that can also refresh your memory. The best instrument for measuring 0.0002 grams of a salt is. So you have analytical balance because the number of decimal places is higher. So what is the major difference? The major difference between analytical and top loading balance. What's the major difference between analytical and top loading balance? What's the major difference between analytical and top loading balance? Pure substances, that we want something that is pure from pure. A pure substance is a homogeneous material that when it contains only one substance is pure. And that means, for instance, when water, if anything is dissolved in there, it's no longer pure. Impure substances contain impurities. It may be or it may be heterogeneous. So really need. So what you don't really need is impurity. It doesn't matter. Maybe you're present in water and you need water. That sugar is now impurity because you didn't need sugar. Anyone you don't need is now called impurities. So it's the one you don't need that is called impurity. The one that you need. So that is the impurity. Then only one component, and what is the aim of separation? The aim is to remove impurity from a mixture or a separation. So that's the aim of separation. So principle in separation. So the relative solubility of the solid in solvent. That if you have a mixture of oil and water, you can separate them using a separation. The oil will be on top while the water is on top. You can get the lighter one and then get the oil later. So separation funnel. So that is why you use a separation funnel. So the absorption the particle that sticks to the surface is called adsorbent. And then the solvents that adsorbent, mostly applicable in chromatography. We have spoken of mixability. They are not mixable. But when you come to chromatography, the important principle is adsorption. Crystal or non-crystal. You can have gas, solid, liquid. We have organic or inorganic nature of the constituents. It also depends on that. We can use whether we can use crystallography recommended. Activity of the mixture is the mixture reactive. So effect of temperature, melting, sublimation, distillation, fractional distillation. You look at differently. Now, difference in boiling point is a fractional distillation. Difference in fractional distillation. That is the principle for use of crystallization method. That's the ability of them to form a crystal. So of what? Chromatographic method. Dash is the principle in the application of evaporating the thing out of it. That could be you are eating, you are looking at evaporation. That means you are trying to make liquid to escape. The liquid is not needed and the liquid will escape. So that is evaporation. And that method, what we call boiling point, because it will at the boiling point, it will considered in the separation of a mixture of ethanol and water is dash. Ethanol and water, ethanol boils at 78 degrees Celsius, while water boils at 100. Heat the container containing both mixture. Ethanol, water remain. So immiscibility or solubility is the basic principle in the separation of mixture. That is why you use the separation funnel. So now, evaporation most suitable when compound with low boiling point. That the ethanol will be evaporated out while the water. Different substances in a mixture having different boiling point. Example, crude. We have petroleum fraction, we have different fraction. When you now that have the lowest temperature will come out first, followed by the one that crystallization, you have precipitation, you precipitating and soluble salt. There are two salts that are soluble in water, such as silver. They are present in water. You want to remove them. You now begin sodium nitrate. You now begin to be able to have silver nitrate precipitating. Salt, but two of them were soluble, but you are removing them by precipitating them out. Techniques based on the flow of materials between the. Now, the materials you want to separate will now be forced to move or pass through a stationary stage, a stationary phase, and the mobile phase is the one that will, and the stream is water is moving in a pipe, so you to where you should go. So that is a mobile phase. Then it will now meet the stationary, and the separation will continue. This is the basic principle of chromatography. The mobile phase. The basic principle is the adsorption. Adsorption is different from absorption. Sugar is absorb water. When you put sugar in water, it absorbs. But it will not be dissolved. So that means it's a different process. Because, okay, precipitation. I've said that when you have two given solvent, you can precipitate one another. Precipitation reaction is reaction of two soluble. Example is silver. Silver nitrate is soluble in water, and therefore, and you can have sodium chloride, which is soluble. The silver nitrate is now insoluble from the solution. Or what your main interest was to have silver chloride and sodium nitrate. They were soluble in nitrate from the solution. The important thing is that you have removed your prefer for the removal. It is a method preferred silver ion from a solution is that is simply precipitation. Precipitation. Silver and magnesium nitrate and lead nitrate electropositive than lead. Therefore, magnesium will be easily precipitated from the magnesium nitrate react with ammonium hydroxide solution. Precipitate dissolve in excess ammonium nitrate react with ammonium hydroxide solution. This is why precipitate does not dissolve in excess ammonium hydroxide. At the end of the reaction, only lead nitrate is present as a precipitate. So that's another example. Magnesium nitrate and silver nitrate. Is a precipitate out of the solution. It dissolves, is more soluble in water, for instance, than silver nitrate. So you can separate them by precipitation. So question, describe how you can separate the mixture of magnesium nitrate and precipitation. Describe how you can separate silver chloride and silver nitrate. That is still by precipitation. The major difference between the adoption of precipitation in the separation of magnesium nitrate and lead nitrate is based on. See the answer for yourself. So lead nitrate react with ammonium hydroxide solution to form what? White precipitate. So this white precipitate does not dissolve in excess of ammonium hydroxide. At the end of the reaction, only lead nitrate is formed. So you can look at that. It's based on the solubility. So that that's what your answer tells you. So of the kinetic molecule, we are now moving to kinetic theory of gases. I want to take you to your secondary school idea. Molecular theory can be used to justify the Dalton law of partial pressure. But first of all, what is the Dalton law of partial pressure? The Dalton law of partial pressure tells you that if there are different gases that do not react chemically, that means we have 3, 4, and all of them are mixed together and they do not react to form a new product. So it's telling you that the total pressure exerted pressure due to the combination of the different gas will be the sum of the individual gas pressure. Maybe gas A has 2, will be 2 plus 3, and the next one have 5. That's 2 plus 3 plus 5, and so on. Please say. So now, where there is a mixture of gases, they do not react chemically. That is Dalton of kinetic theory say that where there's a mixture of gas, they do not react chemically. Sorry, pressure exerted by the gas mixture is the sum of the partial pressure exerted by the individual gases to the one that applies. So can you examine the different kinetic theories, them one after another? So derive the relationship between vapor pressure and relative molecular mass of anything. Okay, that's all right. We will look at relationship between vapor pressure and relative molecular mass of a gas. So the molecular mass in all over mass of one molecule of a substance. Vapor density is mass of certain volume of gas or volume. So what we have here is that 2 times vapor density is the same as relative molecular mass. Vapor density. To calculate the relative molecular mass, you say 2 times the value of the vapor density. Or you have vapor density, you say that vapor density is equal to relative molecular mass divided by 2. So vapor molecular mass, why the relative molecular mass is 2 times the. So those are two different things. There are 2 different things we see. Mass of a gas whose vapor density is 2 units. Density is equal to relative molecular mass. So 2 times 2 is now 4. Given an element is 16 grams per mole, calculate the expected vapor density. So you know that the relative vapor density, so that means vapor density will be relative molecular mass divided by 2, and that will be that's what we have as 8. That's the answer is 8. If the vapor density of a gas is 2.4, is calculate the relative molecular mass of the gas. Force is calculate the relative molecular mass of the gas. The relative molecular mass is 2 times vapor density, so that will be 2 times. Calculate the vapor density of a gas whose relative molecular mass is 28 grams per mole. So the answer will be R. Of diffusion in terms of 1, density of gases, the relative molecular mass of gases, both statement, and show the relationship between them. What is Graham's law? It's talking about factors that affect the rate of diffusion of gas is mass of the gas, then density of the gas. And when we talk about it, say that the rate of diffusion of gas is proportional mass of that gas. So kinetic theory, postulate of the gas, kinetic theory of gases, is a postulate of is that a gas is composed of a very large number of tiny molecules. Imagining gas as consisting of large number of tiny molecules. Gas, you cannot see gas, but you can see it flowing. That means the particles is that very small, far apart from each other. That means that molecules are far apart. That's why you can see gas. In the next one, feel the order. That means the gas molecules are far apart. The molecules are far apart from each other. The gas molecules are considered.
Sorry, sir, which unit is this?
We are just following the unit from 1 down.
You say? Sorry.
I can't say which unit I am now, but what happens is I will start. But you can see some things being introduced to help you understand the higher something.
Okay, I just joined, so thank you, sir.
Okay, sorry. Sorry. When you go to the course page, you will see everything we have done.
Okay, thank you.
Able to download the PowerPoint. So everything is there in the course page. So let's continue. So the of the kinetic theory that consists of molecules, and the molecules are very small, tiny molecules. The gas molecules are far apart from one. A small atmosphere. The size of the gas molecule is negligible compared to the total volume occupied cylinder. You see, it will fill the gas. It's telling you that the gas, the size of the gas molecule is very small. When you look at the one is the second postulate is that gas molecules are confined to a container at rapid random motion. So that means the gas molecule is constantly moving. And that relational motion, they move in all possible directions with different speed. That means gas molecule. First postulate is that all gas consists of tiny particles, and the molecules are far apart from each other. And the size of the gas molecule is very small when you compare to the size of the gas molecule are confined to a container and are in a state of constant rapid and random. So now, can you state the first postulate of the kinetic theory and state the assumption that the first law is that gas consists of tiny particles called molecules. The assumption molecules are far apart from each other. That's one. And that the volume occupied by the gas molecule is very small when compared to the volume. Two things we can get from that first law. Postulate. The next postulate is gas consists of a very large number of tiny particles. You can have is that the gas molecules are far apart from each other too. The gas molecules are considered as the size of the gas molecule is negligible.
Hello, sir.
Yes, sir.
Hello, sir.
Yes,
Yeah,
I'm
what's
hearing
the difference? What's the difference between gas particles and gas molecules?
Gas the same. The particle, when you look at kinetic theory, say all matter consists the gas molecules. It can be molecules or atom, right? Well, the way we are using here is the same. Hello?
Yeah,
Are
I'm
you hearing
hearing you.
me?
Yes,
Concept
I'm
is the
hearing
same.
you.
In this concept is the same. But if you are dealing with sodium, the particle may be different. The particle will be atom, right? But when you are dealing with gases,
yeah, that's what I wanted to.
All right. Okay.
That's exactly what I want.
Mm.
Thank you.
So, and if you are dealing with charged particles, charged ions, the particle is now what you call ions. So the use of the word particle is actually relative. So we now look at the third postulate. We have handled the second postulate. Let's look at the third postulate. During their motion, they collide frequently with each other and with the wall of the container. So now, when gas move, they collide with each other. They also collide with the wall of the container. So now, what is the consequence? We can define two types of collision here. One will be the elastic collision. When a collision is elastic, we say the momentum before collision is the same as the momentum after collision. The collision can be inelastic. That means the momentum before collision is not the same as the momentum after collision. But now, let's look at that third part. During their motion, they collide frequently with each other, and with the wall of the container. So the collision are perfectly elastic. Because they say is assumed to be elastic, it means momentum before collision is the same as momentum after collision. So now, the kinetic energy of the molecule before and after collision is the same. The kinetic energy of the molecule before and after collision, they are the same. That is, the energy may be transferred from one molecule to another during collision, but there is no net decrease in kinetic energy. That's the kinetic energy is conserved. And that's why one of the reasons we momentum before collision, maybe you have the mass of the gas molecule is m and it's moving. So when it is moving, the momentum that is the mass times velocity, that is mv. So after collision, the gas will return. That means what we say that the momentum before collision is the same as momentum in direction. We now have minus m. Now is given as momentum after collision. The change in momentum is defined minus momentum after collision. That's what we call the change in momentum. And that is momentum before collision is mv minus mv. That means the change in momentum is 2 mass of the gas, 2 by the velocity in which it is moving. So you can look at it. That's the third law. The third law talks about collision, and we see that the collision is elastic. The collision is elastic, and because the collision is elastic, momentum before collision is equal to. Yes.
Hello, sir. Yeah.
Yes, I'm hearing you.
I want to get this. Are you saying that when they are operating in a normal atmospheric condition, that's when they are changing momentum is constant after collision and before collision? In the
before
same
collision,
atmospheric condition.
Yeah, that's what we are talking about. We normally condition, standard temperature and pressure. And we now talk about 2 types of gas. Later you shall see that and identify 2 types of gases, ideal and non-ideal gas. And the gas law is specifically applicable to ideal gas. But we are using some models to create what we imagine and then compare to the real thing. Ideal gas. We shall see later that non-ideal gas do not obey all the gas law, and it deviates from the gas model. So, but the model we use here is that then we now amend the model. When we amend the model, we are amending the model to make sure that it now matches what is okay.
Yeah, I get that.
So if the velocity of a colliding gas molecule of mass 0.001 kilogram, calculate the momentum before collision, the momentum after collision, calculate the total change in momentum. The time taken is 0.01. We look at momentum before collision is mv, which is what? Mass times velocity. We obtain that 0. per second. So now, we now have a mass after collision, the momentum 0.002 kilogram per meters per second. Then total change in momentum will be momentum before collision minus momentum after kilogram meters per second. So the rate of change of momentum will be the change, and the time was given by 0.001 second. And therefore, the rate of change of momentum is now 0. meter. So now, what do you mean by the rate of change of momentum? Gram meters, the rate of change, total change in momentum, sorry. The total change in momentum should also have the same unit as meters per second. So the rate of change of momentum will be meters, kilogram meters. Okay, now let's see. No, it will be cancelled. It's kilogram meter. So now, when you look at the rate of change of momentum, exerted is equal to the rate of change of momentum. When you look at Newton's law, it tells you that force is the same as the rate of change of momentum. So what we have calculated here also is them. So the rate of change of momentum of the body. Yes, so you want to ask a question?
Sorry, sir. Can you revise?
Yeah,
I didn't
which
get
of
this
them?
one. The one that
Hello?
you had.
Hello?
Yes.
Yeah,
okay.
I think this solution we are talking based on a gas operating in a vacuum. Yeah, as in all the matters, as in their grams, their weight, they are operating in the same frequency.
Yeah,
so
yeah.
I think it has to be gram meters per second. Because they are weighing almost the same. All the gases are operating on the same frequency, so they are on the same side because of their change of momentum and in collision and after collision. That's what we are trying to get here. Hello.
No, and what happened if you are subtracting 2 grams, right?
Yes.
Do you understand me?
Yes. Yes.
Hello?
I'm hearing
Yeah.
you.
So when you are subtracting a number, a unit does not change.
Yeah. Yeah. I know.
Yeah. So that is why we have that. So, but okay, for the
Yeah.
person,
Rather, it will increase. It won't change.
Sorry, sir, can you go back small? I didn't get these calculations at all.
ask me a question. So of the body was given to you. So, you say what? Is it the calculation that you want to know?
Yes, yes, sir.
Okay, but do you know what is momentum?
You
Yeah,
can't get
yeah.
the calculation here without following the process.
Okay,
Do
okay.
you know what is momentum?
No, no, sir.
Okay, momentum is defined as mass times what? Velocity, right?
Velocity. Yes.
Okay,
Yes, mass
okay.
times
So
velocity.
now look at the equation very well. If the velocity of a colliding gas molecule of mass, the mass is what here? 0.001 kilogram is now 2 meters per second. The velocity is what? 2 meters per second.
Yes.
So calculate the momentum before collision. The momentum before collision will be mass times velocity, which is what? 0.001 times 2. Can you get that one?
Yes, sir.
Yes,
I'm
sir, I will
talking to the
try.
madam. I
Yes, sir,
want
I
her
will
to
try.
understand. No, not try. Multiply the result and see what is the mass. Look at the equation. What is a mass and what is a velocity? The unit of mass is kilogram. The unit of velocity is 2 meters per second, and it's given as 2. So when you multiply, you now have what you call momentum before collision. And now the momentum after collision will be the same value, but it will now be negative, minus, since the other one was 0.002, this one will be minus 0.002. So now total change in momentum will be momentum before collision minus momentum after collision, which is 0.001 minus 0.002 minus 0.002. So that is why you have 0.004. So now
Okay.
0.0004. So now what you call the rate of change of momentum will be the momentum, total change in momentum divided by the time. The time was given as 0.001 seconds. So you divide that by time and you have gotten that. Now, I now bring you to Newton's law. Newton's law states that the rate of change of momentum is equal to what? The applied force. That's what Newton's law states. So now, the rate of change of momentum of a body is proportional to the applied force. The rate of change of momentum is given as 2 times mv all over t. 2 mv, which is the denominator or numerator, is now the change in momentum, the total change in momentum, divided by what? Time. So the rate of change of momentum is equal to applied force. That means applied force will be 2 times mass times velocity all over time. So that's what applied force will mean. Now let's
Okay,
take
I got it.
a kinetic theory of gases. At relatively low pressure, there are no
Hello,
intermolecular.
sir.
Yes.
Hello, sir. I think for
Yes,
that
I'm hearing you.
equation, that is the formula for calculating change of momentum.
Yes.
Change of that is the formula. I just wanted them to understand that's the formula. That law.
Okay. Yeah. Is that
So that
okay?
is the clarification I wanted to. Yeah.
Okay. So now, kinetic theory of gases. At relatively low pressure, there are no intermolecular forces between the molecules. So the theory is assuming that's the fourth postulate. When the pressure is low, the forces of attraction and repulsion between gas molecules is actually not really there. That's what the theory postulates. But in real sense, we will always have forces of attraction and repulsion. So the fourth law said that at relatively low pressure, there are no intermolecular forces between the molecules. And the fifth law said that the fifth postulate said that the collision of gas molecule with a container give rise to the pressure. So what we mean by gas pressure is that gas is moving, colliding with the container with each other. That's why there will be pressure. So that is what gas pressure means. So the pressure exerted by a gas is due to the force exerted on the wall of the container due to non-stop collision or bombardment of the molecule. Because the molecules are constantly moving, they will collide with each other, they will collide with the wall of container, and that is what we mark as gas pressure. What we measure is as gas pressure is the collision, the rate they collide. If they collide very high, it means the pressure will be higher. Look at your car tire. When you drive your car tire, they'll go and gauge your, say this pressure is 40 psi. So it's telling you that that is a collision between the air molecule. Air is a gas there. Now, if you increase your temperature, if the tire is hot, the pressure will be higher. So we will see all this later on. So we have highlighted 5 theories and 5 postulates, and the last one here is the 6th postulate. The absolute temperature of a gas is proportional to the mean kinetic energy of the gas molecule. Now you see one gas molecule A move, and the kinetic energy is 0.2. And the next one move, and the kinetic energy is 0.3. So if we have 2 gases, for instance, 2 gas molecules, the mean kinetic energy will be 0.2 plus 0.3 divided by what? By 2. So the total number. So when we get that the absolute temperature of a gas is proportional to the mean kinetic energy of the gas molecule. Take note, when we come to kinetic energy of the gas molecule, what factors that reflects that is temperature. When we come to the pressure of gas molecule, what factors that reflects that is the collision with the wall of the container. When we are considering collision with the wall of the container, we are looking at gas pressure. And when we are considering the average kinetic energy at which the gas molecule moves, we are considering temperature. Take note of that. And we look at gas molecule consists of tiny particles called molecules. We see gas molecules are constantly in motion, colliding with each other and with the wall of the container. We say that the collision of the gas molecule is perfectly elastic. That means momentum before collision is equal to momentum after collision. But for any collision that is not elastic, momentum before collision and after collision are not the same. So that is what we can see from the postulate. We have highlighted the postulate. So the question, state the kinetic theory of gas that account for the following: temperature of a gas. The average kinetic energy of a gas molecule is measure of the temperature. Elastic collision. And when you call about elastic collision, it's because the intermolecular force between gas molecules are negligible, because it's not very insignificant. That's why we can say that the collision is elastic. Pressure exerted by gas molecule, the collision of the gas molecule with each other and with the wall of the container is a measure of its pressure. So these 3 parameters about elastic collision, temperature, and pressure, you should know the postulate that applies to them. So now let's look at derivation of the gas law. I pray that time will be able to take us there, because I have another class exactly 6 o'clock. So consider a gas moving in a cubical container of size L. If you have a cube like sugar, all the sides are equal. If one molecule of a gas moves from one end to another, the distance covered is what? L. If it moves from one side to another, because all the sides are equal and each side is equal to L. Now, if that molecule now returns, the distance covered will be what? 2L. So L plus L, 2L. The time between collision is given as, when you look at time, the meaning of velocity. Velocity is equal to distance over time. So if you want to make time the subject of the formula, time will be equal to distance divided by velocity. So we have that. So the momentum before collision is now mv. We said mass times the velocity. The momentum after collision is what? Minus mass times velocity. The total change in momentum is what? Mass times velocity minus mass times velocity, which is what? 2 times mass times velocity. So that is one factor we have now said there. So now, from Newton's law, the rate of change of momentum is equal to what? Applied force. So now we can say that force is equal to change in momentum all over time. When we talk about the rate of change of momentum, we are looking at change in momentum divided by time. So now you can recall the time, the fraction we defined about time. We were defining velocity as distance over time. That means time will be equal to time will be equal to what? Velocity divided by this, sorry, we define velocity as equal to distance over time. That means time is equal to distance over velocity. So when we take change in momentum, which is 2m mass times velocity, divided by what? The time. That means the distance over velocity. We will have this, and if we simplify it, we will have m over the distance times velocity squared all over 1. If there are n number of molecules, then the above equation is multiplied by n. N is the number of molecules we multiply here, then we have a force. We now see that the force will be equal to the mass divided the mass, small mass, multiplied by the number of molecules, which is the Avogadro's number. Number of molecules can simply be seen as when you multiply the number of molecules by the mass of the particle, you have what we call molar mass. Molar mass is defined as number of molecules multiplied by the mass. So you can see n number of molecules times the mass of the gas gives you capital M. Capital M is what we call molar mass. So we now see that the force is equal to the molar mass divided by the volume times velocity squared. How do we get the volume? Because when we are looking at the cube and we are looking at the length of the three sides, when you multiply L by L squared, you have the volume. We are coming to that very soon. So now, pressure will be defined as force over area. So if we take that expression for the force and divide by the area, it will be equal to pressure. And that pressure is now simplified to m over L times g squared all over 1 times 1 over L squared. So that is what we have as gas pressure. We can replace the velocity with the average velocity in the x direction. That means gas molecule will move in x direction, some will move in y direction, some will move in z direction. So now when you look at that, we can replace that, and we, instead of having v, 1v, we now look at average velocity, which is v x squared in x direction, where p is the density of the gas. P is equal to, that's rho, is the density of the gas. The rho is the mass over velocity. So that mass divided by or volume of the gas will give you the rho. So I will actually download this video to you. I'm sorry that I may have to increase my speed a little. So where rho is the density of the gas, P is equal to m over v. So v is the velocity of the gas. However, there are 3 possible directions of collision, and one is in the x direction. Some gas molecule direction, and some will move to the z direction, and each direction have separate molecules moving there. So at the end of it, what we expect, because of this difference in direction, what we expect is V, that's the total, the Vx, Vx1, Vx2, and Vx3. And that means Vx in the x direction alone, we will have different gas molecules moving together. So in the y direction, we have different gas molecules moving together. In the z direction, we have different gas molecules moving together. Therefore, we take the average value for each and term the average value, the mean speed. The mean speed is the average value of the velocity of the gas in the 3 basic directions, the x direction, the y direction, and the z direction. Sorry, this one should be Vz. So we take that is what we call the mean speed, the average speed in the various directions, and this can be written as we have sitting here, mean speed Vs squared plus Vy squared and plus Vz squared. So however, Vs squared can be equal to Vy squared, can be equal to Vz squared. That means if they are equal, you have Vs squared, this one will be Vs squared plus Vs squared plus Vs squared. That will give us 3Vx squared. And that is what we have here. So the mean speed can be seen as a 3Vx squared if the container have the same dimension and the 3 gases are moving in the same dimension. What is most important is for you to know the formula for the pressure of a gas, but it just feel that I should derive it from you. Once you know the formula for pressure of the gas, at this level, nobody has it to derive, but those that will be doing chemistry, when you come up, you see us better. So now, the average speed now is 1 over 3 mu squared, because the mean speed is 1 over 3 Vx squared. So substitution for Vx squared gives you 1 over 3 mu squared to the equation. And we have the pressure will be equal to 1 over 3 Nm all over V multiplied by mu square. So PV, if we now take P times this, we have 1 over 3m mu square. So this is a formula you should know. That's what I put in the red mark. Anything you will be expected this time is to calculate based on that formula. So now, derive expression for the pressure.
First, I'll go back. Let me screenshot it, sir.
No, you will get it from the course page. But let
Okay.
me, yes, sir. Okay. So this question.
I think that
Proceed, sir. Proceed, sir.
You're almost taking us.
Take it there. Is that what you mean? Okay. So is that? So I'll continue. So this equation is directly what we have done. It's telling you what we have done. So this question will help you to handle that very well.
Nice. Almost in that equation.
So calculate the change in momentum is simply some of the problems that we have done. So apply the Newton law is simply the problem we have done. The different step involves that we have taken. I have simplified it in this presentation. So ideal gas obey all the gas law, while non-ideal gases do not obey all non-ideal gas, ideal gas do not obey the gas law. So that's the difference between, what's the difference between ideal gas and what is the difference between ideal and non-ideal gases? So the major thing there is the non-ideal gases obey equation of states, such as the Van der Waals equation. Equation of state modify the real gas equation to, let me put it there, equation of state modify ideal gas equation to interpret the behavior of real gases, to interpret the behavior of real gases. So now, explore the relationship between pressure and forces. So that's another step you need to do. I'm just pushing the step. What I have done in derivation, I'm trying to put them in a tablet form so that you can now look at them differently. So ideal gas, we now see N is Avogadro's number, is still the step we have taken so far. Then you can calculate the mean speed of 0.001 kilogram of a gas at 298 Kelvin. Calculate the mean speed of 0.001 kilogram of a gas at 298 Kelvin. Question. That's a question. So all what you need to know is to know the relationship between the mean speed and temperature. So you can now know that. So now this is still part of the derivation. I'll be happy to interact with anybody that has a challenge. So you can see how many moles are present in 0.0032 kilogram of a substance whose molar mass is this. So you can see the number of moles present. Avogadro's number is the number of molecules in 1 mole of a substance. So, and that is equal to that. So ideal gas equation and kinetic theory, PV is equal to nRT. N is the number of moles, R is the gas constant. So these are the different equations we have actually derived. And you can see the last equation tells you the relationship between the mean speed and the temperature. Temperature is T here, and N is the Avogadro's number, M is the mass of the gas. So that one we say calculate the mean speed of that gas. This is the one. Calculate the average translational kinetic energy of nitrogen gas at 300 Kelvin, is equal to this. The solution is given there. So the translational energy is 2/3 K times T. K is what we call the Boltzmann's constant. The volume of Boltzmann constant is 1.3 times 10 raised to the power minus 34 meters square kilogram per second square. So the calculation is actually done there. So these are some few calculations you can do. The derivation is not very important, but those who are strong in math, you can join me to carry out the derivation. Can I take few questions before I leave? Very few, please.
Sorry,
Yes,
sir.
sir.
Yeah, you'll get this slide. Somebody, let me read the test. You'll get this slide. Get it from this course page. You also have the video. You have access to the video. You have access to the video on this. Everything we have done will be uploaded in the course page. Yeah, you can ask me questions, please. Very few.
Sir, I want to ask you about these equations. Like, if they give like this momentum, you will see in course material, you will see many equations. I don't know which one I'll take.
No, it depends on what you asked. Like, for instance, let me give you to one. Let me take you to one. The last one I've asked. Let me take it to one. Let me see. Okay, calculate the mean speed of 0.001 kilogram of a gas at 298. So which one do you use there? There are many equations there. We try to break it down here in the lecturing services. So you can see this equation. The last one can be enough for you. The last one can save that purpose. So it depends on the equation that it has. That's why it's good to practice some questions and also get yourself familiar. Any other question, please? I want to switch to another lecture. So any other question, if there's a question, ask. And I think I will try to create some few minutes interactive sections within weeks. Maybe from next week, I'll try and create time that you can interact. When you read your course materials, if you have problem, we can interact.
Hello, sir.
Any other question? Any other question?
Yes, sir.
Ask now.
Sir, you were talking about this Boltzmann constant. Please, what is it?
Boltzmann constant is a constant derived by Boltzmann. It has a value of 1.38 times 10 raised to the power of minus 34. So that's the value of the Boltzmann constant.
Okay, when is it applicable, please?
Whenever you have a calculation to do and it involves the Boltzmann constant, that's when it is applicable.
Oh, okay. Thank you.
Thank you very much. Have a nice time till next weekend. Have a nice time.
Thank you, sir.
Thank you, sir.
Yes.